Hi everyone. Today we're going to talk about section 11.5. It's or and problems. You might remember back when we um, looked at chapter 2, which was sets, and chapter 3, logic. We saw the words or and again. Or always referred to union, which means, combining. And then ands were the intersections, which is the overlaps. So we're going to look at how or and problems are solved with probability. These problems are referred to as compound probability problems. You might remember back in chapter 3 when we did logic, we looked at compound statements. So those statements had ands and ors. We'll look at or problems first. So if I have a standard 52 card deck, what's the probability of selecting a red card or a king? Take a few seconds to think about it, and then you can follow along. So one of the main things you want to remember is when you have an or, you're going to add. So when I'm dealing with a 52 card deck, if I want to find the probability of picking a red card or a king, or means add. So I'm going to find the probability of red plus the probability of drawing a king. But now, when you are picking cards from a deck, remember that there's two suits that are red. So I'm going to end up using the king twice. It would be the king of hearts and the king of diamonds. So my red cards are 26. The probability of choosing a red card is 26 out of 52. And the probability of choosing a king, there's 4 kings, right? There's the king of hearts, the king of clubs, the king of spades, and the king of diamonds. So that's 4 out of 52. But remember that you already counted 2 of those kings when you counted the red cards, because there's 2 red kings. So what I need to do is I need to subtract out their intersection. So I need to subtract out the cards that are red and a king. And there's 2 of those, the king of hearts and the king of diamonds. So I'm going to subtract out the 2 out of 52. And when you do that, 26 plus 4 is 30, minus 2 is 28 out of 52, which you can reduce to 7 over 13. We refer to this as the general addition rule, which is below. So to find the probability of A or B, we just take the probability of A plus the probability of B and subtract out their intersection. Each of the natural numbers from 1 to 10 are written on a separate piece of paper. The pieces of paper are then placed in a hat, and one piece is randomly selected. Determine the probability that the piece of paper selected contains an even number or a number greater than 6. Okay, see the word or means I'm going to add. So I'm going to add the 2 probabilities. I'm going to first find the probability that you get an even number or a number greater than 6. So that's just going to be the probability of an even number plus the probability of a number greater than 6. But then remember, I need to subtract out any even numbers that are greater than 6. So even number and number greater than 6. So if you have the numbers 1 to 10, what is the probability of choosing an even number? Out of 10 pieces of paper, you have 5 even numbers, right? 2, 4, 6, 8, 10. So the probability would be 5/10. Plus the probability of picking a number greater than 6. So how many numbers are greater than 6 from 1 to 10? 7, 8, 9, 10. So that's 4 out of 10. Now I have to subtract out the ones that I counted twice. So how many even numbers are there greater than 6? 8 and 10. So I'm going to subtract out 2 out of 10, because remember, I counted those already. I counted the 8 and the 10 2 different times. So now when I add those and subtract, 5 plus 4 gives me 9, minus 2 is 7/10. So the probability would be 7/10. If you want to, you can even think of it as a Venn diagram. So remember, we looked at Venn diagrams several times. You've got your universal set. We've got the two events here. One of them's even. The other one is a number greater than 6. And then the ones that are that overlap. So which numbers are even and greater than 6? It would be 8 and 10, right? What are your other even numbers? 2, 4, and 6. What numbers are greater than 6 that are not even? 7 and 9. And then what numbers didn't we use? 1, 3, and 5. So those would be the numbers that are not even and also not greater than 6. Okay, you can pause for the next one and try this problem on your own, and then unpause when you're ready to work it out. Consider the sample space and the example above with the 10 pieces of paper. If one piece of paper is selected, determine the probability that it contains a number less than 5 or a number greater than 8. Okay, so there's that word or. So again, I'm going to subtract. I'm going to add and I'm going to subtract. So here I'm looking at the probability of obtaining a number less than 5 or number greater than 8. So I'm going to find the probability of each separately. So I need the probability of finding a number less than 5 plus, so I'm adding because it's an or, number greater than 8, and then I'm going to subtract out their intersection. So what is the probability of choosing a number less than 5? Well, there's 4 numbers less than 5 out of 10. What's the probability of choosing a number greater than 8? That would be 9 and 10. So there's 2 numbers greater than 8. What's the probability of choosing a number that's less than 5 and also greater than 8? 0. There are no numbers less than 5 and greater than 8. So this right here, since we obtained 0, that means it's impossible. It can't happen, right? So those two events are what we call mutually exclusive, which I talked about in other videos. So they're mutually exclusive events, which just means it's impossible to happen. It's because we obtained a 0. So there are two events that can't occur at the same time. You can't have a number less than 5 and also be bigger than 8, right? So if in that case, you end up with just 0 for that part. So all you have to add is the 4/10 plus 2/10, and you get 6/10, which reduces to 3/5. Okay, and then here I give a little example of what mutually exclusive an explanation of it would be. So let's look at some examples and determine if they are mutually exclusive or not. So if we take a look at this example, it says one card is drawn from a standard 52 card deck. Determine whether the following pairs of events are mutually exclusive and determine the probability of A or B. Okay, so the first example is saying, okay, event A is that you're going to pick a jack, and event B is that you're going to pick a queen. So let's write this out first. First, we're looking at jack or a queen. You want to ask yourself, are these mutually exclusive events? Can you pick out a jack and a queen if you're only picking out one card? The answer is no, right? A jack and a queen are completely different cards, and you're only picking one card. So these are mutually exclusive. They can't occur at the same time. So that means when we subtract, we're just going to subtract a 0. So ors mean add, so we're just finding the probability of drawing a jack plus the probability of drawing a queen, and I'm going to put this in here still, the probability of drawing a jack and a queen. So we know that this part here is just 0 because it's mutually exclusive. You can't draw both. So what's the probability of drawing a jack? There's 4 jacks. So that would be 4 out of 52. Plus the probability of obtaining a queen. There are 4 queens. So that's also 4 out of 52. And then if you add those, you get 8 out of 52, which does reduce to 2 over 13. For letter B, we're looking for the probability of obtaining an ace or a heart. Okay, and I'm not using like A and B or in the last example, A and B. I'm using the letters of the names of the card. So A for ace, H for heart. I think it makes it a little bit easier to follow. Okay, so the first thing you want to ask yourself, is it possible to have an ace and a heart? And the answer is yes, the ace of hearts, right? So these are not mutually exclusive because they can occur simultaneously. So here I'm looking at the probability of obtaining an ace plus the probability of a heart minus the probability of choosing an ace and a heart, which would just be the ace of hearts, right? So how many aces are there? There's 4. How many hearts are there? There's 13. And how many ace of hearts? 1. So when you add that, you get 16 over 52. And that reduces to 4/13. Okay, moving along. How about a red card and a black card? Are they mutually exclusive? So can you obtain a red and a black? Nope, that's impossible. So they are mutually exclusive. So when I subtract out the intersection, there is none. So you're going to end up with 0 for that part, right? Mutually exclusive means the intersection is going to be 0. So what's the probability of choosing a red card? There's 26 red cards. What's the probability of choosing a black card? There's 26 black cards. So you end up with 52 over 52, which is 1. So there's a 100% chance you're going to pick a red or a black card. That's all that a standard deck is made up of. Okay, and then letter D, probability of getting a face card or a red card. So can they happen at the same time? Can you get a face and a red? And the answer is yes. So they're not mutually exclusive. So the probability of obtaining a face card, how many face cards are there? There's the jack, queen, and king times the 4 suits. So 3 times 4 is 12. How many red cards are there? There's 26. And how many face cards are red? So what's the probability of choosing a face card that is red? It would be the jack, king, and queen of the hearts, and then the diamonds. So that would be 6 out of 52. So then if you add them, you get 32 out of 52. And of course, you always want to reduce, and that reduces to 8/13. So that's all about OR problems. Let's look at AND. AND, remember, again, is just intersection, but when you see an AND problem, you're going to multiply. So ORs meant add, ANDs mean multiply. And more than likely, when you look at a problem, if it doesn't tell you the word OR, you can pretty much assume it's going to be an AND problem. So this is referred to as the multiplication formula, and we're always going to assume that event A has occurred when calculating the probability of B, because we're determining the probability of obtaining a favorable outcome in both of the given events. So unless otherwise noted, assume that A occurs and then B occurs in that order. So for example, you've got 2 cards that are drawn now with replacement from a standard 52 card deck. Determine the probability that 2 spades will be selected. So what I'm looking for here is a spade and another spade. Ands mean multiply. So what's the probability that you're going to reach and grab a spade? How many spades are there? There's 13 out of 52. It says that you are replacing it. So you put the card back and you pick another card. What's the probability it's a spade? Well, there's still 52 cards and there still could be 13 of them. So the probability is 13 over 52. Both of these actually reduce to 1/4. So that makes it easier to multiply. 1/4 times 1/4 is 1/16. So the probability you're going to choose 2 spades if you replace the cards is 1/16. Try thinking about what happens if you don't replace the cards now. So if we look at the next example, how is that going to change our probability? So it's still the same scenario. You're drawing 2 cards, but this time you're not replacing. So you're picking a card and then you're not replacing it and you're choosing another one. Determine the probability that 2 spades will be selected. So you're still looking for a spade and a spade, but this time you're going to be replacing the card. So we're still multiplying because it says and. So the first time you reach in, what's the probability you're going to get a spade? There's 13 out of 52. Now you're not returning that card. So that means there's only 51 cards left. And you may also have taken a spade out. So there's 1 less. We're going to assume you took the spade out the first time. So now when you multiply them, you get, they actually reduce to 1/4, and then this would be 4 over 17. So it reduces to 1/17. So what we were just dealing with there were what's called independent and dependent events. And it's very important. So events A and B are independent if the occurrence of either event in no way affects the probability of the occurrence of the other. So for example, rolling a dice and tossing a coin. They don't affect each other, so they're independent events. Now, if you have a deck of cards and you choose a card and replace it, then choose another card, or let's say you choose 2 cards without replacement, which one of those is independent? If you answer the first one, this one here, you choose a card and then you replace and then choose another card, those would be independent events because you're replacing it. So you're not affecting the sample space. It's still the same number of cards and you didn't affect the card that could be drawn the second time. The other, though, when you don't replace, that's called a dependent event, and it's when the probability of the second event is affected by the first one. Let's look at an example. So a medical research study on a new medicine for rheumatoid arthritis is being conducted with 25 patients. After the study concluded, it was determined that 19 patients reacted favorably to the medicine, 2 reacted unfavorably, and 4 were unaffected. If 3 of the patients are randomly selected, determine the probability of each of the following. Okay, so I'm first looking at the probability that all 3 reacted favorably. I don't see the word or there, so we're going to assume it's an and, right? So we're looking at here, basically this means the probability of unfavorable and another unfavorable. Oh, I'm sorry, it's favorable, right? Favorable. So the probability of favorable and favorable and favorable. Okay, ands mean multiply. So all you're basically doing is multiplying all of those probabilities together. Okay, so the first person, what's the probability they reacted favorably? There's 19 that reacted favorably out of how many? 25. Okay, now, that one person, you can't count them twice. So these are dependent events. You only have 24 people to choose from now. What's the probability that the next person would be favorable? Well, we're assuming the first person that you chose was favorable as well. So now there's only 18 of them. And then now you already picked 2 favorable. So that leaves us with only 23 people, and 17 of them would be favorable. So the probability is decreasing each time because your sample space is decreasing. And then if you multiply straight across top and bottom, you get 969 over 2300. In the next problem, it says, what's the probability if the first patient reacted favorably, the second patient reacted unfavorably, and the third patient was unaffected? So what I'm looking for here is probability of favorable times probability of unfavorable times probability of unaffected. So the probability that someone reacted favorably would be 19 out of 25. The probability then that someone reacted unfavorably, so now I have to go back and look. Okay, 2 reacted unfavorably, but remember, we already counted 1 person. So now there's only 24, but there's still 2 that are unfavorable. And then to figure out the number that the probability that was unaffected, there's only 23 people to choose from now, and it says 4 were unaffected. And when you multiply all of that together and reduce, you get 19 over 1725. Okay, you can pause the video and try these last 2. And if you get them correct, it means you're good to move on to the next section. So we're going to use the same information from the last example. We're determining the probability of no patient reacted favorably. Okay, so let's recall something. We know that the probability that someone reacted favorably was 19 out of 25. So in one of the other sections, we talked about how to find not favorable. So remember, all you do is subtract the number favorable from 1. And when you subtract them, you get 6/25. Okay, so now we're not finished though, because we're looking for the probability that none of the patients reacted favorably. So what I'm looking for here is that the first person didn't react favorable. That would be 6/25. The second person didn't react favorable, so now there's only 24 people, and the first one was unfavorable, so that means there's only 5 unfavorable now. And then for the third person to be unfavorable, there's only 23 to choose from, and 4 of them would be unfavorable. So now when you multiply all this out and you reduce, you get 1 over 115. The last one is a little tricky because it uses the word at least 1. So remember, when you see this word at least, we talked about this in the last section. This would be the probability that an event happens at least once is just 1 minus the probability it does not happen. So we already found the probability that it doesn't happen right here. So all I have to do is subtract basically all of the answer I just found in the above. And this is how we would have gotten it. You would have to subtract the probability that none of the patients reacted favorably from 1. And that'll leave you with the probability that at least 1 person reacted favorably. So remember, the inside here, this is just this. So I'm just going to subtract 1 minus 1 over 115, which remember, you could just change 1 into 115 over 115 to make them the same denominator. And you get 114 over 115. So that's the probability that at least 1 patient reacted favorably. Okay, that's the end of 11.5. If you have any questions, please let me know. Remember, there's additional videos on my lab that you can watch, but you're all set to do your homework. Please make sure you're keeping up on the homework, and I hope you enjoy the rest of your day.